All right. This section is for deriving the one-dimensional wave equation. All right, so we consider a string fastened. So the length of the string is L, and the string is fastened with tension. So the tension is T. Okay, tension is T. Okay, and then we want to model the vertical motion of this string by initial diffraction. So we will assume that the diffraction is quite small. Okay, and the motion of the string will be vertical. Okay, there is no horizontal motions. Okay, so they are only vertical motions. Right, and also we assume that the string is perfectly elastic, so that when we force the string vertically, then there is no resistance of the string. All right, so at some moment we will see okay. Right, so we may think about that the string could be right in the the shape of the string is that the okay. This is the x direction. Okay, and the vertical diffraction of the string will be represented by a function u. So u is a function of the spatial variable and also the time variable. Okay, okay. So we have so this is the horizontal. Tension, okay, is T. All right. So now we take so we consider a point, right? X0. Okay, and we take okay, a small portion of the string, and here it's x0 plus delta x0 minus delta x divided by 2, and here is x0 plus delta x divided by 2. Okay, and we go up. So we look at this tiny part of the string. Now we magnify this part here. Okay. And because tension will be at every point of the string, the tension will be in the tangential direction. Okay. So this tension is called T1, and this is called T2. Okay. And we assume this point is P, this point is Q. Okay. So here, this is the point P, this is the point Q. Right. Now, the horizontal tension. Okay. And it's here. So the magnitude of the horizontal tension is T. Okay. As we assume that the horizontal tension is T is kept to be the constant, so that there is no horizontal movement. So the force or the tension force should cancel each other. Okay. Now, and let the angle here to be alpha, and the angle here to be beta. Okay. All right. So, any questions? Okay, and now the T1. So the T1 and the cosine alpha is equal to the tension, the horizontal tension, and is equal to T2 of cosine of beta. Okay. So we should have this equation. Okay. And the vertical tension, okay, the vertical tension would be that because we are using this direction as the positive direction, okay, so that so no horizontal motion implies that, okay, and the net force in the vertical direction, okay, is here, is that the T2 sine alpha minus T1 sine beta, sorry. So it will be T2 sine beta minus T1 sine alpha. Okay. All right. So this is about physics, right? But we're assuming only vertical directions, right? So, all right, so there are some basic assumptions. The string is homogeneous, okay, with mass density rho. Okay, so the unit for the mass density could be gram per centimeter, right? Or gram per millimeter, anyway, so could be here, for example. Okay. But, well, so anyway, you may think about that. So this is the mass density. Which, okay, so with constant mass density, okay, throughout the string, okay. Okay, and we also assume the string, as I say that the string performs a small so we have only small transverse motion in a vertical plane. Okay, so we have only vertical direction, and it's transverse motion because there is no twisting or any other motions. Okay, so just the ordinary transverse motions. Okay. All right, so we have. This is the balance of horizontal tensions, right? So that means no horizontal motion, and the net force would be this difference. Okay. So now we apply Newton's law, right? Especially the second law of motion. So okay, now. So now by Newton's law, okay, F is point mass at the point, okay, and the acceleration. So it is acceleration of the point mass at the time t. Okay. And the point mass, the point mass at this point would be equal to rho of delta x. Okay. So the length of this around this point would be delta x. Okay. And the acceleration would be the second derivative of the vertical motion. Or vertical diffraction, u, the partial derivative, okay. And this is the second partial derivative, okay. All right, so we have this one. All right, so we put, okay, so we put a difference. So this is difference. So we have T2 sine alpha, T2 sine beta minus T1 sine alpha equal to the rho delta x, and second partial derivative of u with respect to time. Okay. Now, when we divide the tension Okay, so we divide by t. So we can, when we divide by t, okay, divided by t, but t is equal to t1 cosine alpha, and also equal to t2 cosine beta. So we can write down cosine beta t1 cosine alpha. Okay, and then we cancel them so that we have tangent beta minus tangent alpha is equal to rho delta x divided by t, and the second partial derivative u with respect to t. Okay, so we have this one. Any questions up to now? Okay. Now, now the tangent represent the slope, right? Of the slope of this tangent T1, so that we know tangent beta is the slope at x equal to x0 plus half of delta x. Okay, and tangent alpha, the slope would be here, this partial derivative, okay, at this point. Okay, so that is the slope, as we know. Okay, and so we can write it t minus t, okay, and we divide delta x, so we move delta x to the left-hand side, and we have t rho square. And this is exactly so by letting delta x go to 0, so we have equal to t right. So this is the wave equation. Okay, so the one-dimensional wave equation is used to modeling a perfectly elastic string with very small diffraction along the vertical plane. Okay. Any questions? Okay, so now All right, so now in this section, we will try to solve the one-dimensional wave equations, okay, by a method called separating variable. Okay. So as in the previous section, all right? So we have model the vibration of a perfectly elastic string okay, so we have okay. All right, so so if we move this ratio constant to the different side, all right, and so we have here, and it is the square of speed. The reason is that t, right, because that so we know t is the, so we look at the dimension, okay. So t is dimension is mass, all right, times the length, all right, divided by square of time, okay. And rho is the mass divided by length, okay. So t divided by rho has unit which is equal to the length square divided by time square, so it's length divided by time take square, so it's the speed of the square. Okay, so we have the square of the speed c. Okay. All right, so we have modeling the vibration, right, by this wave equation. Okay. And to solve it, we need okay, so we need additional physical condition. Okay. Described as follows. One, two boundary conditions. Which says that okay, because the string is fastened at these two endpoints when x equal to 0 and x equal to L, so there is no motion at all, right? And so the vertical diffraction would be 0 for all time at x equal to 0 and at x equal to L. Okay, because so this corresponding to the string is fastened. Okay. Okay, so corresponding to the physical condition that the string is fastened at two endpoints. Second, two initial conditions. At time 0, the location of the string in the vertical plane would be f of x. Okay, depends on the horizontal position x, right? So we have for example, maybe we just use some force. And this could be an initial position of all the of the string, right, at the time 0. Okay. So this function okay. So this is 4x in the interval. And also the initial velocity. So the initial velocity called g of x. Okay. So this is describe the initial position. Okay, so this is the initial position of the string. Okay, and this is the initial velocity. Okay, and the velocity of the point mass around the string. Okay, so you think about that. With initial position, initial velocity, then the string will vibrate in a unique way. So we must have a unique solution by the law of physics. Okay, because in classical mechanics, all the systems are causal. So if you have initial position and initial velocity, okay, then the motion of a particle will be determined. Okay, will be determined for all time point, for all the time, greater than equal to 0. Okay, so that is from classical mechanics. Okay, so that then we must have a unique solution. Okay, so myself by okay, so by classical mechanics, we should have a unique solution. Okay, so now we will try our best to find a solution for that. Okay, so we will try to find a solution. Okay, satisfying the one-dimensional wave equation as well as the two boundary solution, boundary conditions, and the two initial conditions. Okay, so now we introduce a method called okay, so the method of separating variables. Okay, so now it consists 3 steps. Step 1, called separating variables. Okay. So we will let u of xt to be f of x and g of t. Okay, for all x in 0 and L, and for all t. So it is clear, right? It is clear to know why we call this method as separating variable, because we assume that u is a function of x and t, and we assume that it is the product of a function of x and a function of t. So we separate these two independent variables into 2 functions. Okay, so this is called separating variables. Okay, and we try to find that we have such kind of solution. Okay, if we can't find any solution with this form, then we will fail. Okay, it is possible. It is possible if you deal with any kind of partial differential equations. The method of separating variable may be a failure for you. Okay, but of course, for this one-dimensional wave equations, we will be successful. Okay, so that's why we talk about this method in this section. All right, and so now, okay, and right. Okay, so when we take the partial derivative of u with respect to t, okay, so there is no effect on the f function. So you can see this will be f of x, and the second derivative of g. Okay, And how about the second derivative of u, partial derivative with respect to x? So we see we have g of t and the second derivative of f. Okay? From that. And we put to the wave equation so that so we have f of x equal to c squared and the g of t all right. Okay, and the advantage of separation variable is that because they are separable, so now we can move g of t to the left-hand side and f of x to the right-hand side. Okay, and so we have 1 over g of t all right. Equal to 1 over f of x okay, and we decide to move c squared to here. All right, it's arbitration for you to make. Okay, so usually we decide to move c squared to here, and so the left-hand side here is a function of t, and the right-hand side is a function of x. All right, so this is a function of t, this is a function of x, but they are equal. So the only case is that this should be a constant, right? Which is independent of x and t, right? Independent of x and t. This is the only possibility. Okay. So the power of separation variable is that, first of all, it's easy to take the partial derivative. Second is that we are able to really, right, separate the equation, okay, to two parts. Now, this part depends on one independent variable t. This part depends only on one independent variable x. Okay, and by the equality, we know that these two quantities should be equal to a constant, which is independent of the two independent variables. Okay, so that is the power of separation variable. Okay, and with this effort, we turn the partial differential equation, the wave equation, into two ordinary differential equations. Okay. Okay. So now two ODEs. Okay. So the two ODEs. So the first one, right? Because this is equal to k. So we have the second derivative of g, k, c squared, g equal to 0. And the second one is f double prime minus kf equal to 0. Okay? Now we have two second order linear ODEs with constant coefficients and which are homogeneous. And we have a lot of, so we have a lot of experience to solve such kind of equations. Now, right. Now we look at the two boundary conditions give us U0t equal to f of 0 and gt, and U of LT equal to FL and the G of t for all t greater than or equal to 0. Right, so we first look at the two boundary conditions. Now, if G of t is 0 for all t greater than or equal to 0, so if G of t is 0, okay, for all t, then U of xt should be 0 for all x in 0L. All right, and so the solution would be 0, which is trivial. Okay, but we don't want trivial solution, right? So we assume that gt not equal to 0 for some t greater than or equal to 0. So we assume that g of t is non-zero at least one time point. Okay. Now from here, because for some t, gt is not 0, so we have f of 0 is equal to f of L should be equal to 0. Okay. All right. So which are two boundary conditions for f of x. All right, so now, under the separating variable method, the two boundary conditions of the original PDE turns to two boundary conditions for the ordinary differential equations for the f of x. Okay, so we have two boundary conditions for that. And so now we will solve this second order ODE first. Okay. So we solve first, right? With the two boundary conditions in above, namely f0 equal to 0 and the f of L equal to 0. Okay. All right, we have lot of experience, right? So when you learn ODE last semester, if you remember, the material in 11.5, when we talk about the STEM Liouville problem, we have solved such kind of ODE before. Okay. All right. So there are 3 cases to talk about, right? So if k equal to 0, okay. So if k equal to 0, a general solution f of x equal to ax plus b for x in. Okay, so if k is 0, then we have a linear solution. Okay, and so since f of z equals 0 and f L equals 0, so we have, right, f0, so b is 0, and L plus b is 0. So this implies that a equal to b equals 0. So we have a trivial solution. Okay. Now if k, so if k is positive, mu square, then a general solution okay. So general solution is a superposition of these 2 exponential functions. And the 2 boundary conditions okay. So when we look at the 2 boundary conditions, so we have C plus D equals 0, and CE mu L plus DE minus mu L equals 0. So now we form a linear system, right? So we form the linear system. Okay. And the determinant of this 2 by 2 matrix is non-zero. Okay. So that we have only trivial solution. Okay. Because this one is non-singular. Okay, so the coefficient matrix is non-singular. So that's why the solution is trivial. And this implies f of x, x0, a trivial solution. Okay. Okay, so we have only the third case left, which means that the k is negative. Okay, so let's take a break up to 2:20.